This is Algebra 2, Chapter 3, Section 8, in which we will study inverse matrices and work with those things. Before you can work with them, you need to know how to get to them. And the idea behind the inverse matrix starts with what's called an identity matrix. Okay? An identity matrix is a square matrix, so it's 2 by 2, 3 by 3, 4 by 4, so forth, with ones on what's called the main diagonal, and zeros everywhere else. The main diagonal is starting in the upper left going down to the right. So ones on that diagonal and zeros in all the other spots. Ones on this diagonal and zeros in all the other spots. If it were 4 by 4, there would be another 1 right here and a column of zeros and a row of zeros around it. Okay, the identity matrix is pretty boring. Now, what the identity helps us do is get to what the inverse matrix would be. And the formal definition of inverse matrices are two matrices that when you multiply them, you get an identity. So the first question they're going to throw at us is, are we looking at inverse matrices? So here's two matrices, and our job is to figure out if they're inverses or not. Well, to do that, we need to do some multiplying. And remember how we multiplied matrices was the row times the column. 4 times a third plus negative 1 times 1/3. 4 times a third is 4/3. Negative 1 times 1/3 is negative 1/3. And then we did the same thing with the row times the second column. And we just did this a couple of days ago. We did the same thing with the second row times the first column and the second row times the second column. And then either in your head or grab your trusty calculator if you're not very strong with your fractions, compute the arithmetic together, and we get 1 out of here, 0 here, 0 here, and 1 here. This is indeed an identity matrix. So yes, these two matrices are inverses of each other. Okay. Now, to work with inverse matrices, we need to know how to find them. And it's not as simple as just straight division. Okay. Fortunately, for a 2 by 2, there's an easy way to do it. Okay. And it all hinges on knowing where you're starting from. If we're starting from a matrix A, B, C, D, then the inverse matrix, this is the symbol for inverse matrix, all right? It's not 1 over A, although it kind of acts like it, but it's not. The formula for finding the inverse of a 2 by 2 is 1 over the determinant of A, okay, like we did last time. And then you have this new matrix D, negative B, negative C, A. Where did those numbers come from? How did those things get to where they are? The main diagonal values trade places. The A and the D swap spots. The D goes up here, the A goes down here. Okay. The other diagonal, the values change signs. They used to be positive, they become negative. If they used to be negative, they become positive. Okay, they switch signs. And then it's important to remember the 1 over determinant of A part of it. A lot of people will get this part correct, but they forgot this. And so what they have doesn't really work out as an inverse. Okay. Two things to keep in mind. If it's not a square matrix, you can't do an inverse for it. It has to be square. And the other important thing to keep in mind, if your determinant turns out to be 0, the inverse doesn't exist, because 1 divided by 0 is undefined, and you can't do that. So let's find a few inverse matrices before we go to work with them. Okay, we have a matrix here. It's a square, 2 by 2, which is a good thing. First thing I want to do is figure out the determinant. Because if the determinant's 0, I can stop. I know the answer is it does not exist. So determinant, remember we did 3 times -4 minus 7 times 1. The arithmetic comes out -19, so we're okay. We can do this now. The inverse then is 1 over -19 times switch their places. So the -4 and the 3 switch places and switch these signs. And presto, we have an inverse matrix. If you want to, you can distribute this -1/19 into these, and then you would have 4/19, 7/19, 1/19, -3/19. You can do that, that's fine. Right? If you remember this matrix back here, that's what they did. They distributed their fraction into it. Okay? If you want to do that, that's fine. If you want to leave it out here like this, that's acceptable to me. Okay, it's really up to you. Just make sure if you leave it outside, you actually leave it outside. Put it there so that your answer is correct. Okay, let's consider a second one here. 2, 3, -4, 3. Well, first let's find the determinant. Down and to the right minus down and to the left. Cleaning up arithmetic, we get 18. That's not 0, so we're in business. So it'll be 1 over 18. These two switch places, the 2 and the 3. And these two switch signs. So we end up with this final inverse matrix. One more of these, and you can probably guess what's coming. Down and to the right minus down and to the left. That gives us -72 minus -72, which is 0. Ruh-roh. We can't do that. We can't have 0 there. So in this case, the inverse does not exist. Now that we know how to find an inverse matrix, we're going to learn how to use the inverse to get to a solution to a system. Okay, that's the big thing that we're after here, is we're using this to solve systems of equations. So we have a system here. The first thing we want to do is turn it into a matrix equation, just so that we can work with it. To make it a matrix equation, we need to rewrite it this way. Okay, this first matrix, after we did Kramer, that should be kind of jumping out at you, as that's the coefficients. This middle one is the variable matrix, x and y. X was first, y was second. And then the last matrix is called the constant matrix because it's the constant numbers over here. So we have a coefficient times a variable gives us a constant. Now I've copied this and brought it over to the next page so that we can work with it. What we need to do first is find the inverse of our coefficient matrix. So I'm going to come over here and work with that. I need to do the determinant. 3 times 2 minus -6 times 1. 6 minus -6 is 12. So I can do the inverse. 1/12, right, from 1 over determinant of A. The 2 and the 3 switch. The -6 and the 1 change signs. So we have an inverse. Now we're going to take that inverse times the constant matrix. Okay. Now here you have a couple of choices. You can distribute the 1/12 like we talked about a couple of slides ago, and then do the multiplication, or you can do the matrix multiplying first and then distribute the 1/12 in. That's what I recommend. That way you're not carrying around messy fractions all the time. So how do we multiply these matrices? Row times column. Okay. 2 times 3 plus 6 times 9. Negative 1 times 3 plus 3 times 9. Well, now we can clean up the arithmetic. Now if we distribute that 1/12, it comes out nice and clean. We have a matrix of 5, 2. You can give me your answer like this if you want to in matrix form, or you can take it apart and tell me x equals 5 and y equals 2. Okay. Either way works for me. So we worked around matrices, we found inverses, we decided whether they were inverses. We used the inverse to get to a solution. You'll notice we only did this with 2x2s here. There are methods to do it with 3x3s and 4x4s and so forth. They're more advanced than what we really want to focus on in this class. You'll get to do some of that in college level algebra classes. But for our purposes, we're going to stick to 2x2s. If you had questions along the way, hopefully you wrote those down, bring them in with you, and we'll see you in class.